Okay, welcome back to physics. So I wanted to go over how to do this problem where we have a line of charge and we want to find the electrical field at some point that's perpendicular to the center of the line of charge. So this illustrates two of the sort of common, sort of tricks that we do to make sense out of things, and they're going to show up again a whole bunch. So let me walk you through this and get you thinking about it. So what I'm going to have is I'm going to have this line of charge. In this case, let's make it a definite line so it has an end, a start and an end. And what I'm interested in is the electrical field at any point on this line that's perpendicular to it. So again, I'm going to look at a point in space, so a piece of my point in space. And let's see, so I'm going to have this is going to be my x-axis. So let's say this is some distance x in here that I'm interested in. This is going to be my y-axis. And let me see the letter A to indicate this. So I'm going to go from negative a to positive a, right? So when y has a value of a. So a is going to be a constant. So the length of this is going to be 2 times a. So my length is going to be 2 times a. And let's put a charge on there. If q is going to be my total charge that exists across that. So here's what I want to do. So I want to figure out what's my electrical field at this point, so I can plug in any x, and it'll tell me what the electrical field is. So here are the things that I'm going to worry about. So things I'm going to check on. So one, I want to see, I've drawn this, but it's really important that you make this symmetrical. Right. So the way I've drawn this, I'm having my line coming out the center of this, which makes it easy for me then to use symmetry to cancel a few things. And that's the first thing I want to do. So I want to consider symmetry. Can I simplify my life by seeing if things will cancel? Symmetry. Right. So here's what I want to think about. So I'm going to think about having some bit of charge is coming from this side. Let's put it over here towards the top, but not at the top, because that's just too easy, right? So I'm going to have some line of charge that's going to be coming off in this direction. Right? So my electrical field from that line of charge, say this is a positive charge that's here, my electrical field is going to be directed away from that and is going to be in that direction. I'm going to have another area, so I'm going to have another area, an equivalent area, so I'm going to take this the same distance down, so whatever distance y this is, I'm going to take this chunk of charge distance y down, just to illustrate that I can use symmetry to cancel things, right? So again, I'm going to have an electrical field that's going to come from this, it's going to go in this direction, and it's going to point away from that point. And hopefully you recognize that I can use symmetry here. So I'm going to have some horizontal components and a vertical component for each of these. And for each of these, my vertical component is going to cancel. So I'm going to add together my horizontal components. So key thing here, just without doing any math, right? I'm just looking at the arrangement of this and using symmetry to declare that I can just use the horizontal component of these. So here's what I'm going to do. So the electrical field that I'm interested in is just going to be the horizontal or the x component of that. So it's going to be my E, and let's see, let me draw some things in here, right? So I'm going to have in here, I'm going to have some angle. That's going to be the same angle as is in here. So what I'm interested in is the component that's adjacent to that. So this is going to be the cosine angle. Second thing that I'm going to worry about, I don't have to worry about making some substitutions, right? So usually in these sorts of things, I'm going to need to figure out, well, I'm going to have my small amount of charge, and I'm going to have my angle, and dq. Sometimes, like in a ring of charge, I can add that all up and it gets dq, but most of the time I have to deal with that small amount of charge to get it into something that's more sensible. So again, here I'm going to use, I often use density here. I'm going to use linear density because it's a line. So I'm going to use linear charge density to help me get through that. And then the second thing is, right, I have an angle, right, and notice what happens as I integrate, right, as I try to make my dq smaller and smaller, right, dq is going to be changing. But also my angle is going to be changing as I add those up across here, right? So as I start at a shallower angle, right, as I try to go from negative a to positive a, my angle is going to be changing. So I've got two things that are changing as I change y. So I'm going to try to get these in terms of y, And this is where I'm going to use geometry to help me here. Geometry, or trig, I guess. Geometry to help me figure it out. So yeah, let's get into it. These are two common things that we do. So let me think about linear charge density first. So here we go. So linear charge density. So this is our definition of linear charge density. It's going to be the total charge divided by the total length, which in our case, my total charge is Q and my total length is 2 times A. But the nice thing about density, and the reason we like density, is because the density of this whole thing is going to be the density as half of this thing, right? So if I cut this in half, it still has the same density. And if I cut that in half, it still has the same density. So no matter what small part of this I take, it's going to have the same density. So whatever dq I have here, I'm going to have the same density, right? So this is what I want to think about. So I'm going to have this small amount of density, dq, is going to have a small amount of charge over that small amount of length. Well, length here, I'm going to call this dy. So that small amount of length in there, right? So this is just saying the density of my whole thing is going to be equal to the density of my small thing, which is true. But now I've written my small thing in a way that's convenient for me. So I can solve this for dq and get an equation which says this is q over 2a times dy. So I can replace dq with something that's changing with y. Second thing I want to do, let's do some geometry, right? So this is I'm going to have a triangle here, right? So let me look at this blue electric field line. So go back to these numbers. So I'm going to end up having this triangle. So at the top there, right? So as I change this value here, I'm going to have some y value that's changing, and I have this x, which is going to be a constant, right? Because I'm looking for that electric field at this point, and I have some r here. Right? And so I calculate my electrical field by what's the distance to that charge, or the distance to the bit of charge I'm interested in. So let's see if we can get r in terms of x and y. So hopefully you remember Pythagorean. So r is going to be root x squared plus y squared. Looking ahead, I know I had a cosine function in there. So I can rewrite my cosine function in terms of the sides of the triangle. So you remember, cosine is defined as being my adjacent leg of my triangle divided by my hypotenuse. So, well, on this triangle, what is it? So my adjacent leg is x, and my hypotenuse is square root of x squared plus y squared. Okay, so I'm going to plug this all in and see what we get. So we're always sort of starting in the same place. So I'm going to start with my electrical field equation. And you may recall that we define the electrical field, which is going to be some constant, 1 over 4 pi epsilon naught, or k, whatever you feel like using, times the charge over the square of the distance. So this is my formula for a point charge, and electrical field that comes from that. So I'm just going to do the calculus version of this. So that small amount of electrical field is going to come from 1 over my constant, 4 pi epsilon naught, times that small amount of charge divided by the distance to that charge. And hopefully you can see where this is going. Right, so now I'm going to add together my three things. So I'm going to add together my symmetry. So I'm going to put in here the cosine of theta. I'm going to replace the cosine of theta with the geometric function, and dq. I'm going to replace dq with my linear charge function, which then gives me an equation which is going to have only y in there. So here's the challenge, right? So my distance is changing as I integrate up and down that line. My distance is changing, my angle is changing, and my charge I'm trying to shrink down. It's just too many things changing. So I want to get them all in terms of one thing is changing, which I can. Then I can add this all up. So let me write the small amount of electrical field. It's going to be 1 over 4 pi epsilon naught. In dq, I'm going to have q over 2a times dy. Right, so that's in dq. And 1 over r squared, 1 over r squared, so this is r here, so r squared is going to be x squared plus y squared. And I'm going to multiply it by the cosine function, which is going to be x over, I'm going to call this x squared plus y squared to the 1/2. So it's another way of writing square root. So the thing I want to recognize here, what is changing or what's not changing. So in this equation, x is a constant. So I've picked this point here that I'm interested in. Right? I'm going to find the electrical field at this point. But what I'm integrating across is over here. Right? So I'm integrating from minus a to plus a. That point's not changing. So x, the constant, was changing is y here. To get to my total electric field, right now I just need to add up all of these things. So I'm going to have q and x over 4 pi epsilon naught times 2a. And those are all constants, right? I'm going to multiply this by what I have, dy divided by x squared plus y squared to the 3/2. Right? Convince yourself that makes sense. I have x squared plus y squared. I'm multiplying it by x squared. So the reason I've written it this way is that I have constants I can pull out, and this is the thing that I need to integrate. And yeah, I have no idea, right? So what I'm going to do, I'm going to go and I'm going to look it up online. Okay, so I went offline and I went to my favorite. This is the integralcalculator.com, and I typed in this. So notice in this calculator, x is the variable. So in our equation, y was the variable. But we'll figure it out. And I raise it to the power of 1.5, and then I hit the go button, and it comes back with a so this antiderivative that's been calculated. So here we go. So this is the antiderivative. It's going to be my variable divided by my constant squared, root variable squared plus constant squared plus some other constant. So because it's a definite integral, I'm going to forget about this last constant c, because that's going to go away. But yeah, so we did integral math. Let's plug it in here, right? So I take the integral of this stuff, and what am I getting now? So my electrical field now is going to be this constant qx over 4 pi epsilon naught times 2a times this evaluated, right? So what do we say that was? So it's going to be my variable, which is y, divided by my constant squared. My constant here is x squared, times, what do we have? Root x squared plus a squared to the 1/2. And this I want to evaluate from minus a to plus a. So I'm going to add all these up. Add all these little bits things up as I go from y equals to minus a to y equals plus a. So almost there. So now wherever I see y, I'm going to plug in a, and yeah, let's see what we get. So let's see. So I'm going to have my constants q times x times 4 pi epsilon naught times 2a. I'm going to plug in positive a for y. Well, what do we get? I get a over x squared plus a squared to the 1/2. And I'm subtract from that what I get when I plug in negative a. Well, that's the only place it shows up. So minus a over x squared times x squared plus a squared to the 1/2. So when I subtract a negative, the same as adding. So I'm going to get 1 plus 1, I'm going to get 2a on top. So this is going to be q times x times 4 pi epsilon naught 2a. when I combine this together, it has the same denominator, so I'm going to get 2a on the top, and x squared times x squared plus a squared to the 1/2. Right? Okay, let me simplify things a little bit, right? 2a here, 2a there, that goes away. X on top, let's use a different color, right? So this goes away. My x on top will cancel the square here. I think that's all I can do. So I'll end up with q over 4 pi epsilon naught times a over x times x squared plus a squared to the 1/2. Well, let's think about this. So the last thing I want to do is I want to think about this, see if this makes sense. So I can add this up. So does this make sense, the boundary conditions? So when a is really small compared to x, it should act like a point charge, right? So if this shrinks down, I get really small a. So I should act like a point charge. So let's see if that happens. So when a is really small, and it becomes oops, as a goes away, it's just one. So when a becomes really small compared to x, right, it's going to become essentially dropping out. So I'm going to have 1 over x squared. So it's going to be the same as a point charge. So good. And then if I'm right close to this, so if x is really small compared to a, so if x is really small compared to a, right, this is going to be a function of 1 over a, so it's going to be a constant electrical field. Yeah, seems to make sense. I like the other boundary condition better. Anyway, so hopefully you got out of this a few things. So one steps I'm going to worry about. So I'm going to worry about making it symmetrical so I can use symmetry. I'm going to worry about substituting things so I can get to the same thing changing, same variable changing. In this case, I want my y variable changing. So things I worry about, the small amount of charge, so I need to adjust that, and the angle is changing on this one, so I need to deal with that. And then we use geometry and triangles, but it's really the same, always doing the same sort of thing with electrical fields in this case. So I'm trying to use this equation in some way, and then substitute in, so I only have one thing changing. The calculus, right? I'm just looking it up, right? This isn't a math class necessarily. We use a lot of math, but this isn't a math class. But I'm going to look up the integral and be able to use it, and then check my answer so I can catch the mistakes that I make. Hope that's helpful. Talk to you soon. Bye.